Hey everyone, welcome to this explainer. I want you to think back to the days of those totally indestructible brick phones and the unmistakable blocky sound of your very first text message. Well, today we are unpacking the digital DNA of telecommunications. We're going to demystify all that alphabet soup of 2G mobile radio networks, taking some incredibly dense telecom engineering and translating it into a relatable, visual roadmap. Let's get right into it.
So, here is our roadmap for today. We'll be looking at the 2G digital revolution, mapping out the network architecture, breaking down FDMA and TDMA, making sense of logical channels, and then wrapping it all up with security, encryption, and handover.
Starting with Section 1, the 2G digital revolution. This is all about that massive shift from analog to digital mobile networks. We're kicking things off by looking at a truly monumental shift in tech. See, before 2G, the 1G analog systems were strictly for voice and were notoriously susceptible to interference. But the digital era, that changed absolutely everything. Starting in 1991, the GSM standard gave us crisp digital voice calls and the very first SMS text messages. Then, we saw a massive leap in the year 2000 with GPRS, which is often called 2.5G, and that introduced packet data to the cellular world. Finally, in 2003, Edge dropped, bringing us 2.75G and launching us into the era of enhanced, faster data on the go.
Now, look at this dramatic jump in data rates. Early GSM was puttering along at a tiny 9.6 kilobits per second using a circuit-switched method. That basically meant tying up an entire physical channel just for you. But GPRS introduced packet switching, sending data in these super efficient little chunks, which bumped the theoretical max to over 170 kilobits per second. But the real game changer? That was Edge. By swapping the modulation from a 1-bit GMSK to a 3-bit 8PSK, they effectively tripled the capacity per channel. That pushed data rates up to 384 kilobits per second. And get this, they did all of that without even changing the actual radio bandwidth.
Moving right along to Section 2, mapping the network architecture. Let's follow the journey of a call directly from your handset straight to the core.
To really grasp how a call gets from point A to point B, we gotta map out the physical terrain. And it all starts, literally, right in the palm of your hand, with the mobile station, or MS. It consists of the physical phone, the mobile equipment, but much more importantly, the SIM card. Your SIM is basically your permanent, incredibly secure digital passport to the network. It holds your identity, your secret keys, the whole shebang. Without it, the network has absolutely no idea who you are.
Okay, so once your phone blasts out that signal, it hits the neighborhood network tier, the base station subsystem, or BSS. Think of this as having two main parts. First up, the BTS. Those are the actual physical antennas and transceivers you see up on cell towers managing the radio waves. Second is the BSC, which is the controller acting as the local brain. A single BSC manages dozens of those BTS antennas, allocating frequencies and keeping power levels in check.
And after navigating your local neighborhood, your call travels to the big city center of our network map, the Network Switching Subsystem, or NSS. This is the core. It's essentially a massive digital switchboard responsible for physically routing your calls, tracking exactly where you're roaming geographically, and housing the gigantic databases of subscriber information.
Now, this core relies on a highly specialized team working seamlessly together. When you make a call, the MSC acts as the main switchboard. It checks the HLR, which is like a permanent address book, to confirm who you are. But because you're mobile and moving around, you're also logged into a VLR, a temporary guest registry for whatever area you're currently in. Meanwhile, the AUC is handling your security authentication behind the scenes, and the EIR checks your phone's unique hardware ID to instantly block stolen devices. It's a brilliantly coordinated digital dance.
All right, Section 3, Invisible Highways, FDMA and TDMA. Let's dig into the rules of the radio road.
So we've mapped out the hardware, but what about the actual radio interface carrying your voice? How does GSM prevent millions of calls from just crashing into each other? Well, it uses two distinct methods together. First is FDMA, or frequency division. Think of this as giving users completely different frequency highways. For example, the 900 MHz band is sliced into 124 distinct carrier frequencies. Then we have TDMA, or time division. This separates users on the exact same frequency highway by assigning them specific repeating time slots to speak.
And speaking of those time slots, 8 is absolutely the magic number in GSM. One single TDMA frame lasts just over 4.6 milliseconds. Think about how fast that is, and it's divided perfectly into 8 slots. That means one single frequency carrier can support 8 different physical channels simultaneously. 8 users are essentially taking turns so incredibly fast, your ear never even hears the gaps. It's wild.
To make sure everything stays in its proper lane, notice the specific uplink and downlink frequencies for the different GSM bands. This uses a setup called FDD, Frequency Division Duplex. It simply means that your phone uploads data to the tower on one specific frequency block and then downloads from the tower on a completely different one, separated by a really safe margin. This guarantees your upload and download signals never ever interfere with each other.
Next up, Section 4, Making Sense of Logical Channels. These are the specific lanes on our invisible highway.
If the frequencies and time slots form the physical highway itself, the logical channels are the actual painted lanes dedicated to different tasks. The most obvious ones are the traffic channels, or TCH. These are your payload lanes. A full-rate TCH uses about 13 kilobits per second to carry your compressed voice data. Half-rate squeezes that down even further to 6.5. This right here is where your actual conversation lives and breathes.
But honestly, having just traffic lanes would result in total, utter chaos. To keep the traffic flowing safely, the network uses a bunch of signaling channels. The BCCH acts kind of like a lighthouse, constantly broadcasting cell info. The SCH and FCH make sure everyone's internal clocks are perfectly synced. When you initiate a call, your phone essentially shouts out on the RACH, the random access channel. And if someone calls you, the network pages you on the PCH. It's literally an entire invisible language of coordination happening constantly behind the scenes.
Finally, we've made it to Section 5, Security, Encryption, and Handover. Let's see how the network keeps your calls safe and keeps you connected while you're on the move.
Let's explore how this whole thing actually verifies you. Authentication is a really clever 3-step challenge-response procedure. Step 1, the network sends a random 128-bit number, called the RAND, down to your phone. Step 2, your SIM card takes that and uses a secret algorithm called A3 to combine the random number with your permanent secret key, the K, to generate a signed response, known as the SRES. Step 3, the network verifies that response. If it perfectly matches what the network expected, boom, you're granted access.
I actually left this quote in its original French from the engineering text because it just hits the nail on the head. La clé qui ne quitte jamais la SIM. The master secret key, the key, never leaves the SIM card. It is never transmitted over the radio waves. An eavesdropper could only ever intercept the random challenge and the calculated response, which makes it virtually impossible to reverse engineer and steal your master key. Pure genius design for the time.
Okay, so you're authenticated, but we still need to stop people from eavesdropping on your call, right? Enter the A8 and A5 algorithms. The SIM uses A8 to generate a temporary 64-bit session key, called KC. That key is immediately fed right into the A5 encryption algorithm, which aggressively scrambles your voice data over the air interface. So every single session gets a brand new, temporary, unbreakable lock.
So what happens when you're driving down the highway? Your phone is constantly listening to that BCCH broadcast channel we talked about earlier. Step 1, if it detects a new location area identity, it knows you've moved to a new region. Step 2, it silently sends a location update request to the local MSC and VLR. Step 3, the MSC updates the central HLR so the wider network knows what city you are actually in, and importantly, it assigns you a new temporary ID to protect your privacy.
Now, if you cross a boundary while you are actually on an active call, the network performs a handover. Notice how the network elegantly delegates this responsibility based on the scale of your movement. If you just switch time slots on the exact same tower, the local BTS handles it. Switch towers but stay under the same controller, the BSC manages that. But if you drive across the city to a new controller, the main MSC switchboard has to step in. The managing entity scales up depending on exactly how far you travel.
But the absolutely crucial thing to remember about 2G handovers is that they are hard handovers. Unlike later 3G systems, which sort of softly blend signals together, GSM physically breaks the connection to the old cell a fraction of a second before establishing the connection to the new cell. It's quite literally a break-before-make system, but it's executed so incredibly fast that you almost never drop a syllable of your conversation.
Well, there you have it.
We've unpacked the foundational 2G architecture, from the sheer magic of 8 time slots and logical channels all the way to secure handovers. This tech literally laid the groundwork for modern telecommunications. 2G introduced the digital DNA that powers the 5G networks we rely on today. Looking at how incredibly far we've come from 9.6 kilobits per second, it really makes you wonder, what impossible leaps will the next generation bring? Thanks so much for joining me on this explainer. I really hope it brought some clarity to this amazing tech. Keep exploring, and I'll catch you next time.